In this video, we're going to look at polynomial functions. We're going to examine some of their attributes. We're going to look at how they behave, and we're going to talk about what are called zeros of polynomial functions. So we're going to start with how to recognize a polynomial function by its equation. So really there's two criteria. One is that the coefficients must be real. Okay? And if the coefficients are real, that just eliminates one thing, imaginary coefficients. Okay? And the other thing that we want to know is the exponents need to be whole. What does it mean to be a whole number? Okay, a whole number is a counting number or zero. So 1, 2, 3, 4, 5, Elmo numbers plus 0. So what does that mean it cannot be? Okay, that means there are no fractions. There's no decimals. And there's no negatives for the exponents to be whole. Okay, so we're going to look at these examples of functions and decide if they're polynomials or not. First one, f of x is equal to 13x to the fifth minus 2x cubed plus pi x minus 15. First, take a look at your coefficients. 13, negative 2, pi, negative 15. Are they real? Well, do you see any eyes up there? No imaginaries? Then they're real. You may be tempted to say pi is not real, but it is. It's irrational, but it's real. Okay, so that's okay. Now let's think about your exponents. Exponents. Are these all whole numbers? What's the exponent there? That's going to be a 1. And really we can think of this as x to the 0 power, okay? So if I look at all my exponents, they're all whole, so we are good to go. This is a polynomial. Okay, how about this one? 15 divided by x minus 12x squared plus 10. Is this one a polynomial? Okay, well let's look at my coefficients. I think this one could be written as 15 times x to the negative 1, right? So my coefficients, 15, negative 12, 10. All my coefficients are real. That's good. My exponents, negative 1, 2, and 0, right? X to the 0. We have a problem, right? That negative means we do not have a polynomial. Our exponents need to be whole, so this is not a polynomial. All right, next one. 19x to the 7th minus 28i x to the 5th plus 22. Okay, so let's look at our coefficients. 19, negative 28i, 22. Oh, that I gets in the way. Not a polynomial. And last, we've got the square root of 10x cubed plus 2x minus 13. Coefficient, negative radical 10, positive 2, negative 13. Are my coefficients real? Yes, they are. Are my exponents whole? Yes, they are. So yes, this one is a polynomial. All right, moving on to the next criteria. We're going to look at polynomial functions and trying to decide whether or not they're polynomials by looking at their graphs. So the graphs have two criteria. Here we had two criteria with equations. The graphs themselves have two criteria. Polynomial graphs are both smooth and continuous. Okay, smooth means no jagged edges or corners. And when we're talking about being continuous, we are thinking no holes or jumps. Okay, so let's look at this first example, this graph. We have something that goes down, up, Do we see any kind of jaggedness? No, we see this wavy kind of aspect. Do we see any holes or jumps? No, so this is definitely a polynomial. How about this one? Smooth, definitely smooth. But my gosh, I had to pick my pen up way up here. There was a jump from this side to this side of my graph. This is not a polynomial. Okay, how about this one? Straight down, straight up. Looks like a corner to me, so this is not a polynomial. This one. Nice wavy characteristic, no holes, no jumps, just very smooth and continuous. This would definitely be a polynomial. Okay, so the next thing we're going to look at here is end behavior, or what's called a leading coefficient test. It turns out that polynomials are very predictable. They all follow the same kinds of criteria when it comes to the end behavior of the functions. So first of all, what is end behavior? What do we mean when we say end behavior? Well, what we mean by end behavior is what does a graph look like on its ends? It does not refer to anything that's happening in the middle of the graph. If I have something like this, we would not care about anything in the middle here. We would care about what's going on the left-hand side and what's going on the right-hand side of the graph. So on this one, we would say that the graph is falling on the left and it's rising on the right. Well, it turns out polynomials follow a pattern. And we can use some of our prior knowledge to help us remember what that pattern is. So there are two things that you need to keep in mind when we're talking about end behavior. One is the leading coefficient. Is that leading coefficient positive or negative? So leading coefficient is a factor. And then the degree is also a factor. So our degree we're looking at, is our degree even or odd? Okay, so if your degree is, so let's consider something where we have a positive leading coefficient and an even degree. Well, this is going to behave the same no matter what the degree is and no matter what that leading coefficient is, as long as they follow those criteria. As long as the leading coefficient is positive and as long as the degree is even. Well, I think we already know a function that is that way. We know that our quadratic function, our base quadratic function, looks like this. And this is y equals x squared. A positive leading coefficient and an even degree. Well, what's happening on the left end and the right end? Both of them are rising. So we have rise left and right. Okay. What if the degree is even, but the leading coefficient is odd? Well, I think that's a lot like this. Y is equal to negative x squared, which we know looks like this. Well, what's going on there? Falling left, falling right. Okay, so now let's think about something where the degree is not even, but it's odd. So there's lots of functions that is true of, but the easiest function is our linear function. If you think about the equation y equals x and y equals negative x. Your degree is 1 and 1, odd, odd. But here we have a positive leading coefficient and here we have a negative leading coefficient. Here it's like this, here it's like this. Okay, so let's think about that. What's happening on the left? It falls left, but it rises right. For this function, what's it doing on the left? It's rising. So it rises on the left, but it falls on the right. One thing that is probably good to recognize is when you have an even degree, both of your behaviors, both of your ends are going to do the same thing. But when you have an odd degree, both of your ends are doing something different. You've got one up and one down. Maybe this way, maybe this way. We need some music. Just kidding. Okay. So now let's apply this. We want to find the end behavior of this polynomial. Negative 7x to the 4th plus 4x to the 5th minus 2x plus 12. Okay, so we are interested in the leading coefficient, which is the coefficient of the first term if this equation was in standard form. And we notice right away that it's not in standard form. But if it were, this term would be the first term. This is the only thing that matters. We don't care about this or this or this. It's just this first term. So I want to think about, is my leading coefficient positive or negative? And is my degree even or odd? We have something odd, which means we have one of each thing going on, right? Little dancing thing. And we have a positive leading coefficient. So that means it's going to behave like this. Okay? Positive leading coefficient, odd degree. So what's it doing on the left? It's falling left and rising right. Okay? This one is a little more complicated. This one hasn't been multiplied all the way out like this one has. So if we want to take the time to multiply it out, we could. However, we don't really need to think like that. We can think about just what would the first term be. Well, we definitely know that this outside monomial, 3x to the 4th, is going to be multiplied by the highest power when I expand this thing is going to be x squared. We can think of it as x squared. And then what is the highest power when I multiply this all the way out? I think this is x to the, is that 5? Getting right up on it, it's hard for me to see. So when I multiply these things together, I have negative 3 x to the 4th times x squared times x to the 5th. I'm going to add these exponents and I'd have negative 3x to the 11th. Odd power, negative leading coefficient. Odd power means one of each. Negative leading coefficient means it's falling, okay? So on the left-hand side, we start up and we go down. So it's rising on the left and falling to the right. All right, coming over here, we're going to look at finding zeros of a polynomial. And what is a zero? A zero is another name for an x-intercept. I'm reaching really high. So as you already know, you could find your x-intercepts by setting y equal to 0 and solving for x. So let's find the zeros of these polynomials. Okay? If I set y equal to 0, I'm really putting a 0 in here, correct? So this is going to become a 0. So let's get rid of this 3 by dividing everything through by 3, and I would have 0 is equal to x minus 5 squared times x plus 4 squared. So I'm just going to set each of these factors equal to 0, and I would find that my zeros are x equals 5 and x equals negative 4. Okay, same idea here. We're going to set this equal to 0. Let's divide out the 1/2. We don't need the 1/2, and we end up with just x plus 2/3 times x minus 5 cubed. Okay, so my zeros are going to be, when I set each of these equal to 0, x equals negative 2/3, and x is equal to 5. All right, those two were pretty easy. They were already in factored form. This one, not factored yet, so we actually have to factor it ourselves to find the zeros. 0 is equal to x cubed plus 5x squared minus 9x minus 45. Any ideas on how to factor this thing? 4 terms, highest is a cubic. What's the first thing you should try? Grouping. Let's try grouping. Let's look here. X squared times x plus 5. Keep this sign minus. What's the leading coefficient, or I'm sorry, bad. What's the GCF of 9 and 45? I believe that to be 9, so let's take a 9. Now I'm going to divide out that negative 9 from negative 9x, and I would have x. Take that negative 45 and divide out the 9, and I'd have plus 5. Perfect. So I have now x plus 5 as a GCF of these 2 blocks times x squared minus 9. Oh, I think this one factors a little further. 0 is equal to x plus 5, x plus 3, x minus 3. All right, so x is equal to here, negative 5, x is equal to negative 3 here, and x is equal to 3 here. So my zeros are negative 5, negative 3, and 3. All right, we'll pick it up next time with some more fun with polynomials.